All right, so last time we talked about sort of the basis of some of these dimensionless correlations for convection and where they came from. Today we're going to talk about how we use them, right? So there were basically two correlations or two types of correlations that were most important. The top one here is the drag coefficient. So for a given shape, the drag coefficient, which is the dimensionless form of the drag force, is a function of only the Reynolds number. And for a flat plate, you might be interested in the average friction coefficient, but that's really the only time it wouldn't be the drag coefficient. And then the Nusselt number, so the average Nusselt number for a given shape is a function of Reynolds number and Prandtl number. And also a function of Eckert number if viscous dissipation happens to be important, but typically we ignore viscous dissipation, so only Reynolds number and Prandtl number. So to use these correlations is, I think, pretty simple, probably something you learned in a previous class, but we'll go through the basic steps. So the first step is basically trying to understand what correlation you want to use. So there's all different correlations, and you need to understand which one applies to your particular problem. And some of the questions you have to ask yourself are: is this a forced convection problem versus a natural convection problem? Is it an external flow versus an internal flow problem? Am I far enough away from the vapor dome that nothing is going to condense or evaporate, so I'm single phase, or do I need to start thinking about two-phase correlations? And then, of course, what's the geometry? So what direction is the flow going, and how is it approaching the surface, and what does the surface look like? So these are, I think, usually pretty obvious, but certainly you need to get that straight in your mind so you can go and get the right correlation. You have to determine the fluid properties that are required, and typically you would evaluate those properties. If they depend on temperature, you would evaluate them using the film temperature, and the film temperature is just the average of the surface temperature and the free stream temperature. That's not always the case. There are a few correlations where you would evaluate them using the free stream temperature, and then there's some kind of a correction based on Prandtl number or viscosity. But if you're using a correlation like that, it will usually be pretty obvious. Most of the time, you just use the film temperature. So then you got to calculate the dimensionless quantities that are required by the correlation, right? So the correlations require Reynolds number for the drag force, right, and Reynolds number and Prandtl number for the Nusselt number. So Prandtl number is a fluid property. That will be one of the properties that you calculate up here in step 2. Reynolds number you do have to calculate, though, and it's defined always the same way here: rho times the characteristic velocity times the characteristic length divided by mu. There's a couple of fairly common ways to screw this up. One way of screwing this up is by not being careful about what the characteristic length is for the flow situation that you're dealing with. So somebody came up with these correlations, and when that person came up with the correlations, that person also basically specified once and for all what the characteristic length is going to be for that object if you want to use his or her correlation. So you got to make sure you're using the correlation, the characteristic length that is appropriate for the correlation. And if you're not sure, then you need to make sure you're reading the background literature or looking at the function information or whatever it is, so that you can figure that out. Once you've got the Reynolds number and the Prandtl number, then you have everything you need to access these correlations, right? Reynolds number and Prandtl number. So you have to go get the Nusselt number and the drag coefficient. And this is, there's all different ways of doing this. If you have a handbook that is filled with charts, you might actually just pick numbers off of a chart. A lot of times there's equations that capture these relationships. I'll show you how you can pick these out of ease by using the heat transfer library in ease. So this is ease. This is a program that we'll go over in a second. This is our example for today. But if you go up here under options and then you click function information, if you come down here to heat transfer and fluid flow, you'll see that there's these libraries. We've talked about some of these, but the ones that will be particularly important for the next couple weeks is convection. So if you go to the Convection Library, this is just basically a library of convection coefficients or convection correlations for fairly common geometries and flow conditions. So if we go here now at the bottom, you have another drop-down menu, and you can select between some of the different questions that we talked about, right? So internal flow versus external flow versus natural convection. Here we have an external flow problem. We have, we might have flow over, in our example, it'll be flow over a sphere, flow over a cylinder. So if I let's click on non-dimensional here, you have, if you scroll through here, flow over different shapes, right? So there's a whole bunch of different shapes here, but they all kind of have the same, They all have the same protocol in terms of calling them. First of all, they're all procedures, right? So you would do call and then the name of the procedures, and then you'd have this list of input parameters, right? And so we know that the dimensionless quantities that we're trying to get are a function of Reynolds number and Prandtl number. So for us, the input parameters are Reynolds number and Prandtl number, and then there's a colon, and then there's a list of the output parameters. So for these external flow correlations, the output parameters are the Nusselt number and the drag coefficient, right? So here's the Nusselt number and the drag coefficient. So you would call this, you would put in a value or a variable that has a value for the Reynolds number and the Prandtl number, and it would go off and figure out for you, based on some correlations that are programmed in it, right, what the Nusselt number and the drag coefficient are. And if you have any questions about where those correlations came from, or maybe what the characteristic length should be that you use in the Nusselt number and the Reynolds number and things like that, you can always click on information and it'll bring up a window that will tell you those things. But this is how you access correlations in ease. And like I said, there's other correlations for other different conditions. The other thing I should mention here is that this is the non-dimensional correlation, and this makes a lot of sense given what we've just been talking about, right? These are actual correlations for Nusselt number and drag coefficient in terms of dimensionless Reynolds number and Prandtl number. But if you look up one, there's dimensional correlations, and this is a little bit different. So if you look here now, there's a whole bunch more inputs, right? There's fluid and temperatures and pressures and everything like that. And then the outputs are drag force and heat transfer coefficient, among other things. So this is kind of a wrapper for the dimensionless version, right? This function will take these inputs, it will calculate the Reynolds number and the Prandtl number, it will use the non-dimensional version to calculate the Nusselt number and the drag coefficient, and from that it'll give you back the drag force and the heat transfer coefficient. So they go together. This is in some ways a lot less work than the other one, but this non-dimensional one is certainly much more close to what's actually going on, and you should understand the difference between the two. So I guess the last step then is once you've accessed the correlation, you'll have the Nusselt number and the drag coefficient. You have to use them. So you'd use them to calculate the dimensional things that you're interested in, typically the drag force and the heat transfer coefficient. So let's do an example to illustrate how these things work. So here's the example I came up with. We have a droplet injector. So we are injecting droplets downwards. All right, so in the direction of gravity, the droplets have diameter 200 microns. What else here? We have an injection velocity, so the velocity that they leave the nozzle at is 5 meters per second. They leave the nozzle at 800 Kelvin. Here are some properties of the droplet material. So this is the density of the droplet and the specific heat capacity of the droplet. They're falling through air, and the air is at 20 degrees Celsius. So we need to determine the velocity, the temperature, and the position of this droplet as a function of time. So as it falls after it leaves the nozzle. So I guess by assigning this a single temperature, I've already sort of implicitly made the assumption that I can lump together all the material inside of this droplet and put it at one temperature. That implies that the BO number is small, so I can use a lumped capacitance approach. I should check that at some point to make sure that's true, but it's a small droplet. We're going to assume it's very conductive, and so I'm going to assume that that's true. So we'll do this in ease. So let me find that. So here are the inputs. This is just the inputs to the ease program, right? We have the diameter, temperature at the beginning, and then some properties, the air temperature and the injection velocity. So I'm going to use a numerical technique to solve this problem. I'm doing that because the heat transfer coefficient, the drag force, those are going to be functions of velocity. They're going to be functions of the temperature. So all of this is going to be, kind of complicated, and to solve this analytically is probably actually not even possible. Instead, I'm going to use a numerical approach, and we talked a lot about how to solve transient problems numerically. And the thing that I hope that I focused on enough that it's clear is that the starting point is to figure out what are your state variables. So in our typical lumped capacitance problem, our state variable was just one temperature, and we needed to figure out a state equation that would give us d temperature, d time, and we could integrate that through time using any of these different numerical integration techniques. For this problem, it's a little bit more complicated. We have three state variables. We have velocity, position, and temperature. So in order to move through time using whatever technique I want to use, I need state equations that are going to calculate for me du dt, so this is the rate of change of velocity, this is acceleration, dx dt, so the rate of change of temperature, and d temperature, d time. And I need to be able to calculate them given some arbitrary values of u and x in temperature and I guess time, right? So we're going to take the approach that we took previously where, let's see if I can go back. So here I am going to set initially some arbitrary values of those state variables. So this is x equals 0, this is right at the nozzle. This is t equals t initial, again right at the nozzle, and u equals u inject. So this is the initial value of those state variables, and I'm going to make sure then that before I move on and try to integrate anything through time, I can actually calculate those state equations, right? I actually have a dx dt, a dt dt, and a du dt. And once I have that, then it's just turning the crank. I can use any of the techniques that I've talked about previously and get a solution, right? So here I have those three things set. Let's go back here. The first state equation is actually really simple, and that is that dx dt, which is the rate of change of position with respect to time, is just u, right? So if I know u, I immediately know dx dt, right? And that's what I programmed right here. Okay, so dx dt is equal to u. The next one is less simple, right? So now I'm going to try to get d temperature, d time. I get that in the same way that I did for a lumped capacitance problem, which is that I do an energy balance on the droplet. So I'm lumping it all together. The energy terms are q dot convection is entering, right? At least I've drawn it as entering, and du dt is the rate of energy storage inside of this system. So in is q dot convection equals out, which is nothing, plus du dt. So that's what I did here. For q dot convection, I'm using Newton's law of cooling. So h bar times as times t infinity minus t, right? It's into the control volume, so it's t infinity minus t. And then this is rho times v times c. So this is the thermal mass of this object times d temperature, d time. So if I look at this, temperature is one of my state variables. So I know temperature. This gives me dt dt, which is the thing I'm after. Other things that I know include T infinity, that was 20 degrees. I know the density and the specific heat capacity of the droplet material. The surface area is easy to calculate given the diameter, and so is the volume. The thing I don't know in this equation that I absolutely need is the heat transfer coefficient, right? So up until now, the heat transfer coefficient is something that has been given to you, but now you'll actually have to calculate it based on what the situation is, right? And so that gets back to using the correlations. This is a simple enough problem. This is flow over a sphere that it's been studied to death, and people know exactly how it works, how it behaves, and there are plenty of correlations out there for you to use. You don't have to do your own CFD analysis or experiments or anything like that. So let's remember how to use the correlations. First thing we got to do is identify the flow conditions. I hope this is pretty clearly an external flow problem, right? If I go back here, there will be a thermal boundary layer forming around this sphere, but as long as there's no other spheres in the vicinity that could impact that thermal boundary layer growth, this is going to be an external flow problem. It's a forced convection problem, right? Because the flow is dictated for you. It's falling, right? It's not a natural convection problem. So I'm going to want to use a correlation for external forced convection over a sphere. I got to get some properties. So I use the film temperature, which is the average of T infinity and T. And based on that, I can get any of these properties here. These are, I hope, obviously the properties of the air, right? I put a little A on here, A subscript, to delineate them from the properties of the droplet. One of the ways that people screw up these problems all the time is they'll use the wrong density or the wrong conductivity when they're calculating the different dimensionless parameters. So there's usually going to be multiple densities and conductivities floating around. You got to make sure you're using the right one, right? So here I'm using the density and the viscosity, the specific heat capacity, the conductivity, and the Prandtl number of the air, right? That's what I'm going to use to calculate these dimensionless numbers. And so if I go back and look at my ease program, that's what I've done here, right? This is the film temperature. These are just calls to the property routines in ease to get the density, viscosity, specific heat capacity, and conductivity of the air, right? Air. All right. So I have to calculate the dimensionless number required by the correlation. So this is going to be the Reynolds number. The characteristic length to use for the Reynolds number for flow over a sphere is the diameter. If I didn't know that, I would go look it up, right? And so the easiest way to look that up might be to go to options, function information, and then just hit info here. And do that over here. Right here, it's telling me that the way I would calculate the Reynolds number is with the diameter, right? So it's fine if you don't know that. You're not expected to memorize it, but you have to, if you don't know it, you have to go look it up. So that's the Reynolds number. You'll notice I'm using the density of air here, not the density of the droplet. Now I have the Reynolds number and the Prandtl number. I can go access the correlations, right? So to access the correlations, we'll just go back to that function information, convection, external flow, non-dimensional, and I'm just going to paste this call right here. So I'm going to call this external flow sphere ND procedure, give it the Reynolds number, the Prandtl number, and it will give me back the Nusselt number, the drag coefficient. And that's what I did right here, right? So at this point I have, once I run, I'll have the Nusselt number and the drag coefficient. And then the last thing I need to do is use the drag coefficient and the Nusselt number to calculate the drag force and the heat transfer coefficient. So that's what I did right here. This is the heat transfer coefficient. So couple things again. One is whatever characteristic length you use for the Reynolds number, diameter, that's the same characteristic length that is used to define the Nusselt number, right? So you got to make sure you know what it is and then use it consistently. Two is this conductivity here is not the conductivity of the droplet, it's the conductivity of the air, right? It's an easy thing to screw up. So at that point, then I have the heat transfer coefficient, and I have everything I need in this equation to calculate the rate of temperature change. And so that's what this equation is. And I find that the rate of temperature change is right there. It's apparently cooling off very quickly. It was injected very hot. There's a relatively high heat transfer coefficient right here. So it's cooling off really, really fast. All right, so let's see. I have, where am I at here? Oops. At this point, then, I have 2 of the 3 state equations done, right? I can calculate du dt. No, I'm sorry. I can calculate dx dt. That was just u. I can calculate d temperature d time. I did that with an energy balance. The last thing I need to do is calculate du dt, and then I'll be done and I'll be ready to integrate through time. So to calculate du dt, I just do a momentum equation, and we talked about a momentum equation the other day when we were deriving the x momentum equation for our convection equation, right? And we said that momentum doesn't balance. Instead, you would write that the rate of momentum in plus the sum of the x forces has to be equal to the rate of x momentum out and the rate at which x momentum is being stored. So this is a momentum balance, and I can apply it to any control volume I want, right? In a couple lectures ago, I applied it to a differentially small control volume to get a partial differential equation. Here, I'm just going to apply it to the droplet, right? So this droplet is my control volume. If I think about momentum crossing the boundary of this control volume, well, if the control surface is moving with the droplet, then there's no mass transfer across it, so there's no rate of momentum in, and there's no rate of momentum out. So now I have to think about x forces. So I'm going to define x as being down in the direction of gravity. That's the direction the droplet was injected. So the forces this thing includes gravity force, right? So gravity force is pulling it down. That's in the positive x direction. And there's a drag force that's actually trying to push it up, right? There's a drag force that's opposing that motion. So that's in the negative x direction. So those are my x forces. And then over here, the rate of change of x momentum, right? So the rate of change of x momentum, you have to remember that x momentum is equal to the mass times the x-directed velocity, right? We think about x-directed velocity as being the x momentum per unit mass. So the x momentum this droplet has is its mass multiplied by its x-directed velocity, m times u. So in this particular case, the mass isn't changing, so I can pull that out, and I just have m times du dt. So if I take these terms and substitute them into this balance right here, I get that, let's see, there's no x momentum in, so that's 0. The x forces include a positive x force, which is gravity, and then a negative x force, which is the drag force. And then this rate of x momentum change is the mass, which is rho times v times du dt. So I know everything in this equation except for the drag force. And the drag force I have to get using the correlations. Of course, I've already used the correlations, and sort of what came along for the ride when I used the correlations in ease is I not only got the Nusselt number, I also got the drag coefficient. So I can calculate the drag force right here. And that's what I'm doing right here. Right, so it's the drag coefficient times 1/2 rho u squared. Just to be clear again, this has got to be the density of the air, not the density of the droplet, right? And then this is the velocity at which the droplet is falling. This area is the projected area of the droplet, right? So it's the area of the droplet that you would see if you were looking at the droplet in the direction that the air is approaching it. So in this case, the air is approaching the droplet from below. If I looked at the droplet from that direction, I'd see a circle. And the area of that circle is pi r squared, which is right here. So I have everything I need then to calculate that drag force. And that's what I've done here, right? Projected area, drag force. And then the last thing I have is the du dt. So if I solve, I should now be able to find the temperature d time, that's one state equation, dx d time, that's another one, and du d time. So that is the rate at which the velocity is changing. In this case, apparently I injected this thing at higher than the terminal velocity, and therefore it's actually slowing down as it falls. So I think I'm done then in terms of the heat transfer part of the problem. At this time, I just need to integrate these state equations through time, and I can use any numerical technique I want. Explicit ones would be a little easier than implicit ones for this particular problem, but whatever you'd like would work. I'm actually just going to use the integral command in ease because I think that's the easiest way to do it. So in order to use the integral command in ease, what I'll do is I'll come back here and I will comment out these state equations, or these state variables, right? So now if I try to solve, it won't be able to solve, right? I don't have enough unknowns. So instead, what I'll do is I will put in these integral statements, right? So I have that here, u is the initial velocity plus the integral of du dt with respect to time from 0 to, I'm going to simulate 2 seconds. T is the initial temperature, integral of dt dt, and x is the initial position, which is 0, times plus the integral of dx dt, right? And so these are going to be moved through time together in little time steps. You'll notice that you can't do these integrals unless every one of these integrals that you're trying to do together have the same integration variable and also the same limits, because ease is moving these all together through time, okay? And then the last thing I did here is put an integral table that keeps track of time and x and u and t. So hopefully at this point, if I hit solve, somewhere there's an integral table. Here's my integral table, and it has time in one column, and these are all the time steps it decided it needed to take. And then over here I have x and u and t. So I can make plots of position, velocity, and temperature with respect to time, or other things if I want. I could plot velocity versus x. Here I plotted droplet velocity and droplet temperature as a function of time. So temperature is this, let's move this. Temperature is this black line, so it starts out very hot, and then it cools off to ambient temperature. And velocity is this blue line. It starts out moving at 5 meters per second, and then it approaches its terminal velocity as time goes on. So that's a pretty sophisticated model, actually, right? And it was done by using correlations, which are, I think, pretty easy to use, pretty simple to understand, and then using what we now know about how to build numerical models of transient problems, which I think is also pretty understandable.